thanks John for or the organizer, because that's the first time I will see people actually wanted to get up to see category theory. So that's amazing. So anyway, what I want to do is cover small little topics here and there, depending on how fast we can go, and it's better that you just stop me when you have questions, but I think it's better to cover less material, but better than more material. But anyway, for people who haven't seen this before, that might look like I'm going a little fast, and I'm doing this on purpose, because otherwise we won't be able to cover so many ideas in 3 days. So my aim is at the end, you know enough words and you have some general ideas that you can go and read yourself about category theory and how to apply this to Haskell. Yeah, so that's it. The other different thing is, most of category theory books and courses are aimed for mathematicians, because those are the people who invented this. But I'm trying to make this for programmers. So instead of trying to prove stuff and trying to, do theorems, we're going to try to build the stuff. So we are going to try to see how we can express what the category is in Haskell, in Scala, and how you can build all these concepts actually in your programming language. Actually, it turns out that writing these programs and proving the stuff in mathematics is the same thing, because we have this nice carry-over correspondence. But anyway, that's the aim. But anyway, even if you don't understand anything at all of what I'm saying, I would like you to go back home with two main ideas of category theory. The first one is that composition is the most important thing. So we usually do... No, this is not working. We usually draw a lot of diagrams like this, where we say, well, we have something like a type A, a type B, and a type C, and we have functions, f and g, and we can compose them to get like one thing going directly from A to C. But the important thing is not only composition, it's composition that works. There is some kind of typing in this. So this is one of the first core ideas. The second core idea is that anything is not really like something in itself. It has the only way it gets its identity. Oh, sorry. It's by the relations they have with other things. For example, we will see later that this is what we call a product. And it's not important that this is A times B or whatever. The important thing is that you have all these different functions that will have some laws attached to them. And the fact that this is what we call a product. The network of relations, not the object, but how things fit with themselves. So anyway, I will get started. Let's see how far I can get today. I'm very old style, so I will do a lot on paper. But anyway, so what is a category? So that's the first thing we need to know in order to study all of this stuff. So if you have a category, it's just a bunch of objects. So we usually call them like with capital letters, and a bunch of function, arrows, morphisms. You can use the name you want. And each of these arrows, I will use arrow as the general thing, has a source object. So one of these is the source of the arrow and goes to the target, or you can also call it domain and codomain. There is like a lot of terminology. So this is the data we need. So if you look here, I'm defining a category in Haskell, and you can see I have two arguments here. The O is the objects, and then we have the M for morphisms, for arrows. And as I said, every morphism has a source and a destination. That's why it needs to have two objects as arguments and get you back a type. If you don't completely, so this is the Haskell I'm using is pretty advanced. You actually need GHC8 to run all of this. But again, the important thing is the core ideas. So this is the first things we need for a category, but we also need two more pieces of data. So for every object, actually, we need to have an identity arrow. Well, I'll call it identity X. So this is something which goes always from x to x. So this is what I have below. So that we have the identity which goes, if you have a morphism, for every a to a. And we also need to have a way to compose two functions, two arrows. So if we have some f going from a to b, and some g going from b to c, we have to be able to compose it to get something going from a to c. And what the identity is, what the composition is, what the objects are, and what the arrows are, completely changes in every category. So at first you can intuitively think of types and functions, but we will see later that this is just an intuition. There are many more things which fit into this idea. Okay, so we are almost done. There is one extra thing we need to have that I haven't shown in the Haskell code, which is that this thing has to obey some laws. And if you've been in Gabriel's talk yesterday, you will already recognize this. So if you have the identity and you compose it with some f, you need to get the same f, the same. And then you have this law which says that it doesn't matter how you compose things, because any order is okay for composing functions. So everything for which you can sort of find this description such that these laws are respected is what we call a category. And this is the main object of study. So one extra thing, you've seen here that I'm using this kind of arrows diagram. So this is also something which category theorists gave to the world. So this idea of how to represent these notions as diagrams. So when we draw a diagram, now that you know what a category is, we usually omit a lot of information because it would be very redundant. So even if I write something like this, so these are the objects, we draw the objects as dots, and then these are the arrows as arrows. I won't draw the identity arrows because they always exist, because this is a category, and I won't draw every composition except when I need to focus explicitly on this. So if you look at this category, this doesn't have two arrows, but two arrows, the three identities, and the composition. So we actually have 6 arrows in this category, even though we only draw 2 on the diagram.
A question?
Yes?
So this looks very much like a monoid, right? So what's the difference?
We'll see that, that will be my second example. A monoid is a special case of a category, a very simple one. So, okay, so what's the simplest thing if you are programming to get a category? You can say, well, my types will be the objects and my function will be the arrows. And that's what I have here. In Haskell, we usually call this the category Hask. So if you read somewhere that, oh, Hask is blah, 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 then you know that it refers to this category. And thanks for the latest version, you can actually define this in Haskell. So the first argument is the object, so it's going to be types. And the second argument is the arrows, which in this case will be the normal functions in Haskell. And the identity is just the normal identity function, and the way you compose things is just the normal composition operator. Okay, so this is like the simplest thing you want. If you are doing mathematics, instead of types and functions, you usually start with sets and functions, but it's mostly the same. The second thing we can see is that a monoid is actually a special case of a very simple category. So if you have a monoid, and remember that a monoid was, I will run out of paper very soon. If I draw smaller, could everybody see at the end? I will try, and if you don't see, just shout at me. So a monoid is just some kind of set or type where you have some notion of a zero element, of an empty element, and some way to combine values. So you can think like combining is a function of this type, and the 0 is just an element of m, and you have the associated laws with monoids. So how can you look at this as a category? So here's the trick. You take one object, one single object, which doesn't represent anything at all. It's just the single object of this category, and then for every element in M, you take an arrow. So this is kind of weird. So imagine, for a more specific example, that we have numbers, so integers, with the 0 and the plus. So the way you transform this into a category is by having just one single object, and then number 0 is an arrow, number 1 is an arrow, number 2 is an arrow. And then when we compose stuff, so the composition of two of these things, so the way you, it's actually using this append operation. So so the composition of the arrow 1 and the arrow 2, because we are in the monoid plus, is the arrow 3. And also because we have this 0 can work as the identity arrow. So that's the trick. So here your arrows actually represent objects in your type, which is sort of weird the first time you see it, at least for me. But we can actually write this also in Haskell. So we can just, I have here just one type, it has one single object, which is called 1, and then this monoid morphism, which is just a way to recall the M. So if you see, so this is the name of the type, and then this is the way we can construct one of these monoid morphisms, and you see that you construct it by giving me an M, one value. So the 0, the 1, the 2, and if we want to make this into a category, we can do this, that's in the top, we can do this if M is a monoid by saying, well, the empty element is the identity, and if we want to compose two things, we just use this append operation. So this is, yes?
Can we just maximize the screen?
Yeah, it was because I think somebody right there couldn't see.
Oh.
Yeah, better. So the first way you can think, so now we have at least two intuitions of what a category is. We have this intuition which is just like types and functions, but they are also some kind of generalized monoids, because a monoid is just a category which has one single object, and actually every category with one single object will be a monoid. So you can think like, if we want to have this, it's like you have a monoid, but you cannot compose every value with themselves. You have some kind of restriction. You can only compose these two things together and these other two things together. That's another way to think about it. Actually, you can also think of orders in elements as categories, and here the trick is slightly different. So if you have some kind of set and you have an order on it, you have all these rules about what this order should look like. So the first thing you usually have is that x should be less, I use less than or equal because that's the right intuition, it's less than or equal than itself. And also that if x is less than or equal than y and y is less than or equal than z, then x is less than or equal than z. So wait a minute, this also is a category, because you have, this notion of composing two things together and this notion of identity. So if you want to do this in category theory, what you do is you say, well, now my objects are going to be the elements in M. So imagine, again, I'm using integers as an example. So you have 1, 2, 3, and so on. And I will have an arrow only if one thing is smaller than the other thing. So I have an arrow from 1 to 2, an arrow from 1 to 3, an arrow from 2 to 3, and so on. And if you compose things, this is just like having transitivity. Yes?
So a question here is, in the case of the first one, right? Where
Yeah,
you had
the monoid.
So the arrows themselves, you are representing as integers, right?
Yes.
Here the arrows are the actual...
the arrows
functions.
are like are like the proof of the relation. So the fact that 1 is less than or equal than 2 is what the arrow represents.
I see. So that's the part I'm not getting. Is in one case it is the
Yes.
number itself.
Yeah, that's why I'm showing these examples, because once you start doing category theory, you should try to get rid of this intuition of what an arrow is, because you think of functions, but here it's completely different, and here this is completely different. So one of the so one of the good thing of this field is that it's generalized in such a way that it covers all this kind of different stuff.
Question.
Yeah.
So in the case of the monoid, we have only one object.
Yes, exactly.
And I kind of missed the conceptually you were talking about what the single object is and what the arrows represent. Can you go over that again?
Yes. So here, actually the single object means nothing. So you cannot have like intuition what it is.
Right.
And the way you can see this is actually in a monoid you can compose any two values. So if you remember, the object would give us is a way to know when we can compose arrows.
Right.
But because in this case we always can compose them, they have to go always on the same object because that's the only way we can compose them. If we have two of them, then there would be an element of the monoid we could not compose with it.
Okay.
Okay. So these are just some examples. There are a bunch more if you read any book on category theory. I also have some more examples about Haskell type classes, but I don't really have the time to go over it. So I will. But yeah, as part of the talks, I have also some exercises prepared for you if you want to, have a little mind exercise. So I will post the link on the Slack. Okay, so this is what a category is and why you should forget the intuition of sets and functions. So the second thing we do is think of what I was saying at the beginning, this kind of relation between objects. And the one we like the most is the ones we call universal constructions. So this is actually a technical term. I won't go over why you call it like that way. I will just show some examples. But these are the ones we like because they have very, very nice properties. Yes?
So typically, in case if objects have relationships with each other, any relationship, it could be part of a category.
Yes, actually, if you have a set of elements and relations between them, they also form a category. Yeah, that's another way you can get one.
Okay.
So in the category with integers and the append, is there anything that represents the relation of being able to combine them together?
Well, the fact that you have only one object, that is what allows you to combine everything. Because if you have a monoid, everything can be combined with any other element.
That's a dot.
That's the dot. That's why we have one single object. Yeah. Okay, so now we're gonna try to think. Okay, what is a product of two things? So what does it mean to have something which holds two values? So the way category theorists thought about this is, okay, let's think of an object D. We don't know yet what it is, but we want this D to somehow conceptually represent a product. So if we have a product think on Haskell. So the first thing we have is actually, so want to say D is the product of A and B. So what are the things we have? So first of all, we need to have two functions which allow you to get back each element of the pair. So this could be like first and second in Haskell. In category theory, you usually call this pi1 and pi2, but the name doesn't matter. But this is actually not enough to convey what is a product, because everything which gives you an A and B could be a product, but something which holds an integer and an A and another A and a B and gives you randomly one of those A's is something which fits into this diagram. But this is not what we want to have as a product. So the trick we do here is the following. So let me first draw the diagram and then. So imagine we have another C. That's another object, and we happen to have two functions f and g, two arrows, which goes from C to A and from C to B. We are able to build one arrow which sort of goes from C to the product of A and B. I will show the code in Haskell to be more clear. But so when we define a product, what we say is we need to have these two functions to get back the values. But also, if we have any two arrows going from C to A and from C to B, we can actually build a third arrow, which I don't know how to call it, but in Haskell you usually call it F3, Ns, and G, which goes to the product and D. So let's see how this looks in Haskell. So let's try to define what a category with product is. So this is the thing telling you what is the product. So because we need to give it a name for this. And then we have these two arrows. So this arrow, so remember M is like the arrow goes from the product of A and B to A. And this two goes from the product of A and B to B. And then if we have an arrow from C to A and an arrow from C to B, we can build this arrow from C to the product of A and B. So that's exactly what the diagrams are saying. So that's, I found actually this is one of the best ways to explore category theory if you're a programmer. You can try to get a diagram and try to write the concept as a type class. And I'm just showing Haskell to be faster, but I have the code in a Scala here too. So you can see sort of the same thing. So the F is the arrows and the P is the product. So you go from P of A and B to A and from P of A and B to B. So basically every language where you have higher kind of types, you can do this. So this is what we call a product. Great. So any question about what a product is or this whole idea of having these diagrams? Okay, so now we are almost done to what category theories like to do. So I'm just calling it D. But why didn't I call it A times B? Well, nobody's telling me that this thing is actually unique. It might be the case that you have two different objects in your category which work in this way. And if you think about it, if you have Haskell, for example, the product of A and B could be the pair AB, but you could also use the pair BA and just, say that the first is actually the second, so that the way you get the projection is actually getting the second, and the first you get the second projection is getting the first element of the pair. And this is actually something which fits into these diagrams. What is nice is that this, if you have these two things, they will actually be isomorphic in a technical way. So we say two objects are isomorphic if you have arrows from A to B and from B to A, and the composition is the identity in any. So you can basically go back and forth and you go back to the same thing you got, and the other way around. And you can, what you can see is that these two things are unique. But what is better is that you can actually do this proof as Haskell code. So let me go below here. So here, instead of saying every category has the product, a specified product, I'm saying here with this type class where this is a category with some objects and morphisms and some notion of product. But I'm not fixing it. So I'm fixing it in every instance. So we can prove that the product is unique by doing this thing. Imagine we have a category with a product P1 and we have a category with a product P2. We can actually build an arrow going from the product P1 to the product P2. And this is the code, which you can just try to follow the types and it will type check. It's how you get this is something you have to think about a bit more. I have some exercises for you to think how you get this. But if you can see that if you go the other way around and you say P2, P1, you actually get the other direction. And proving that this thing is actually an isomorphism is a bit more complicated, so I won't go into detail why it is. Yes?
So in this case, A and B in the last one, where you the definition, yeah, those are two products, right?
Yes, in this case, what we will find out is that if we have A and imagine this thing and this thing, this will be isomorphic. So you can you can think of, in this case, switching the pair.
Right.
But this works for every category with products. So
they're not the same A and B in the previous diagram.
Yeah, it should be like D prime and...
yeah, it will be like D prime. So you will have a D prime here going from A and B, and a D prime here with this whole thing. And you can see that D and D prime will be isomorphic every time. So you don't have to prove products are unique because they are already proven for everything. And so again, this is actually giving us a lot of information, because in Haskell, products are this usual pair thing, but in other categories these are completely different stuff. And if you think like, well, what is in a monoid or what is in a relation? So if you try to explore this yourself, you will find out that there are many notions in mathematics that or in logic that fit these diagrams, and you can actually say, well, these are all unique, because we know in every category every product is unique. So this is the first example of an universal construction. I will show you another one, and actually what I would like you to do is that you get this notion I will show you. It's much easier than this one, and you try to come up with how you define this in Haskell and how you can prove these two things are unique. So the notion is what we call an initial object. So an initial object is just one object, A, such that for every other object in the category we have a unique arrow to it. So we usually write this thing when something is unique. And that's what we call an initial object. So you can think that an initial object looks like there is an arrow for every other object in the and of course from A to A we have the identity. So there is also an arrow from it to it. So that's what we call an initial object.
You're saying that for every single other object,
for
there's
every
an arrow from A.
Exactly. For every other object in the category, we have an arrow from A to this thing, and then we call this A initial.
So this is true for any category, or is it?
No. So the fact that you have a product depends on the category. There are categories where you have products and some where you don't have it. There are categories where you have initial objects and where you don't have them.
Okay.
But the fact is that if you have products, then they are unique, and if you have initial objects, they must be unique and they must obey a bunch of laws. So it could be nice if you try to find out what is this. So for example, in the case of a relation, which is I think the best one to see what the initial object is. So remember, our arrows represent that something is less than or equal than some other thing. So an initial object is like the minimum of this thing, because for the minimum element, it's always less than or equal than any other thing. So this is an example of an initial object in a different category, and how this all subsumes, this notion subsumes a lot of other ideas. So, okay, let me see how much time I have left. Okay. So, again, I know I'm going fast. Just poke at me in the hallways if you have questions or whatever. So this is universal construction. There are many of them. So you have terminal objects, you have notions like equalizers, ends, a lot of them. But they all have like the same idea. You have a diagram and there's some notion of uniqueness between these two things. But there is something which I've only found in category theory which is very interesting. So imagine you have a category and then you swap all the arrows. So you know, everything which goes from here to here now goes in the other way. So you can see that this is again a category, because, well, if you swap everything and you redefine composition to think, in fact, that this swapping is done, you get a new category. So that means for every category, you can build this other, what we call the opposite category. And you can do this also for any of these diagrams. So I would like you to try to see what the opposite notion of a product is. We also usually call opposite stuff either dual or co-something. So what co-product is. So if we have a co-product, remember we have this D and A to B, but now the arrows are flipped, so they go in this way. And the same way we had this, but now the arrows go in this direction. So what does this notion represent? So what does a coproduct mean? So we must have some kind of way to get either an A or a B and inject it into D. But also, if we have a function from A to C and a function from B to C, we can somehow compose and have a new function which is going from the coproduct to C. So if you think a minute about it, but you will find out that this is what we call a sum type or either type. So in Haskell, this will be something like either AB. So if you have an either AB, you have left, which goes from A to either AB. You have right in this way. And also if you have a function from A to C and a function from B to C, you can get a function from either AB to C. If it's the left, you apply this thing. If it's the right, you apply this thing. So, and because we know coproducts are also unique, we know that this is actually what a coproduct means in Haskell. And if you think what a coproduct means, now I was saying, if you have initial objects, you can also turn the thing around. And what you would get was what is called a terminal object. And in the case of relation, instead of the minimum, this will be the maximum, because you have an arrow going there all the time. But what is more interesting is that this thing called duality is even better, because every time you prove a result in category theory, it also holds for the dual of it. So imagine we say something like, a category with products has unique products. So we can just flip all the arrows and say, a category with co-products, because this is how we flip the arrows, is unique. So every time we have some notion, we just make the co, and we get a new theorem, which is true, just because there is a theorem saying that every sentence which is true for categories is also for the opposite categories. So this is something which is really, really nice, I think, from category theory, that you can take any notion and try to explore what it is with the arrows flipped, but you only have to do the work of trying to have the intuition of what this represents, because all the theorems will come for free, because you've already proven them for products. You don't have to prove them for co-products. So this is duality. So actually, as part of this is one of the most advanced exercises I'm proposing to you. You can try to build the notion of what the opposite of a category is in either Haskell or Scala, and try to prove that if a category has products, then the opposite has co-products. So that it would be in, yes?
So does that hold to say, for example, that if a category has initializers, then its dual has initializers?
No.
No. So if the one has initial objects, then the opposite category will be warranted to have terminal object, which is the dual notion. So you have to.
So not the same statement, but.
No, you have to flip every arrow in everything you say. So if you say the opposite category has the opposite of an initial object, which happens to be a terminal object, and there are some notions which are actually their own opposite, like isomorphism. So for this, you don't have to flip everything, but you have to flip every arrow you find. You just flip everything. Okay, so
so kind of stepping back to product to then like illuminate co-product again. I'm just trying to clarify an arrow from like C to A cross B. Is that's analogous to a function that explicitly has an ordered pair as an output?
Yes, that if you so let me show it here. So this is how you build the usual product in Haskell. So the product type would be just the usual tuple, and then how you compose f and g is by applying the same function, the two functions to the same argument. That's how it would look like here. Yeah.
So the co-product being an ordered pair as input and a single
not an ordered pair, the co-product will have a co-product. So it's not an ordered pair, it would be either of A and B.
Okay.
That's how it looks like.
Right, so it has nothing to do with like a monoid like plus.
Sorry?
Or,
I didn't get that question.
is it maybe I'm missing monad for monoid, but isn't plus like a, because it's a...
Yeah, you mean like the sum type, yeah. That would be the co-product, yeah.
Oh.
So like A, I'm using either, but some people usually write this as A plus B. So that's two names for the same thing, and some people write sum AB. For some reason, and this is something which is difficult in category theory, people make up their names, but these don't generalize. So everybody likes to say this, and then you go and you find some people from some fields of algebra, and they say, I don't like this, I want to write A cross in a circle B, whatever. Yeah. So you have that's just something I'm telling. It's difficult because everybody wants to make their own notation. Does it answer your question?
No, it's. I mean, it certainly helps. The either A, B into C is, I guess, different from how I was conceptualizing plus, because I have like a closure conception of plus. So,
Okay.
But that's. I think that like moves outside of like the question of product versus co-product.
Okay, maybe we can see it later and try to figure out what's the difference.
Sure.
Okay, so yeah, we have 10 minutes. Oh, no, okay, we have 13, so I can answer a question in 3 minutes.
These objects, do they represent types or do they represent inhabitants of text values?
No, so in the case of Haskell, these objects represent types which are inhabited by things.
Okay.
So yeah, this is one kind of usually one kind of ways to get categories. You have types or sets which contain things themselves and then functions between them. So that's what they represent in Haskell. But
Okay. So in that case, then when we have a category with a uniqueness, unique, what was it? I forget the name, but do they all have to be unique types?
you mean unique?
Like initial value.
Unique,
say.
right.
Yeah.
So unit is an issue.
Yeah. When I say unique, this is not really unique in the sense there is only one. Is that if we have two of them, they are isomorphic. So it might be that there is more than one initial value, and actually you can build several of them. If you have like two types and they look the same, I don't know. I have either, but I could also define my own data or AB, which goes from heart A or I don't know, sun B. and this is a completely different type, so it would be a different object in the category Haskell.
Okay.
But these two things have the same structure. They are isomorphic to each other. So that's what I mean by unique. Not unique in the sense there is only one, in the sense that every two of them, so if you have two of them, they must be conceptually the same. Okay? Yeah.
How did you actually prove that the uniqueness held for the products? You said you had proved in the code, right?
Yeah, so what I'm showing this is that if let's assume I have two products, P1 and P2. So I will build an arrow going from the product using P1, like P1 A of B, and P2 A of B. And that's the way I build it. So this is the arrow that I'm doing. That's why I'm proving it, because I'm giving you one part of the isomorphism, and you can switch P1 and P2 and you will get the other part. So as I said, I'm not showing the whole thing because you will still need to prove that these two things make the identity when you compose them. So you need a bit more things here. And this is actually you cannot do in Haskell easily. You could do this in Agda or Idris, any independently typed language where you can encode things like that. But I think this is still, in order to prove uniqueness, you actually need to look back at what product is, and when we say there exists this one, the product actually is stronger. We say that this thing must be unique. So it's not that for every f and g we can build this, it's that for every f and g we have one way to build this. And that's basically what we have the rest, because so I will just tell you the rest of the reasoning. So we have this product P1 and P2, and we know that this we do this, and then we say, well, imagine we have this D prime, so we can go from A and B, but we can say instead of any C, let me use the other product B. So I will get this. So this is, and I will use here pi1 and pi2. So I know that this arrow is not that it exists, it's actually unique, and that's what I'm building there. So it's pi1 and pi2 composed in this way. Now, because I have this arrow, and you can think of switching this, and I have D prime and D the other way around. So the thing is, we can compose these two things because we have D going to D prime and one in the other direction. Now, these two things are unique, and we know that if we have a D, there is always an identity. So because these things are unique, and we know there is the identity, it has to be equal to the identity, because that's the only thing we have somehow. So that's how the reasoning ends if you want to prove these two things are isomorphic. Okay? Okay, so the next notion is, now you don't usually see categories in your Haskell code, except if you use Edward Kemet packages, I guess. But you usually come up with functors. So functors are just mappings between categories. So if we have two categories, and I will just write this with these weird letters, as mathematicians like to do. These two things are categories. So we want to define a mapping between categories. So that's what we will call a functor. So what do we have to do? And if you think about it, it's not very difficult to come up with what a functor is actually. So this has objects, and this has objects. So we need a way to map objects from C to objects from D. So we need a mapping of objects. This thing has arrows, and this other thing has arrows. So we need to map arrows to arrows. So we need a mapping of arrows. But does any mapping of arrows actually make sense? No, it doesn't. So if we have something, so we have an arrow F from A to B, what seems natural if you map the arrow, so we usually don't write parentheses as we do in Haskell, no parentheses. So if we apply the functor to this arrow F, we want to get from what the functor did to A to what the functor did to B. So from f of A to f of B. So this is a law that any functor should respect. But also we have laws on every category. So we have an identity and we have composition. So we need to preserve them. So we have to say that if we map an identity, this has to be an identity again. And if we map a composition, then we can also we can either do the composition and then map, or do it the other way around. So that's what the functor is. So it still looks a bit different from what we have in Haskell. So just wait for a minute and try, and then we will see how this corresponds to the usual notion in Haskell or in Scalas or cats and all of that. So, okay, so let's think of simple examples of functors. I have some here. So, one is the constant functor. So, it goes from a C to a D, and I have to tell you what it does on objects and what it does on arrows. So I will tell you for every object in C, the result will be a constant element in D, so 1k, which is always the same. And now for every arrow, I have to tell you how this is mapped. So if you look at all the laws, there is only one single way in which you can build this and obey all these laws, which is say, for every function, we give you back the identity of k. And then all these laws are respected, because f of whatever will be the identity, so this will be respected. And the composition of two identities is the identity again, so this law will also be respected. So this is an example of a functor. Ooh. Yeah, ooh. I'll need to start using the back of the paper. Other things we can do. So we have a very nice example of a functor, which is the arrow functor. And this will be very important later, so try to remember this. So what we do is we take an object, so again we are from C to D. And basically we take an object D in D and we sort of always make a function from D to this other thing. So basically if we have an object, f of A will be D to A. And now we have to think about what it does to arrows. So I have the drawing here.
Sorry, wait. You take the object from C, and then you map it to what?
To the function from D to A. So in Haskell, we'll see it later, but in Haskell, function types are also types, so they are also objects. So I'm mapping every A to the function from D to A.
Okay.
And now, if we have
sorry, basically the function you don't mean morphism here. The object in D will be the function between.
Yeah, it will be a different type, which is which is the function type. Yeah. And now we have this. We can actually, so we have a function A to B. So now, if we apply f to A, what we will get is something like this from D to A. So this is f of A, and f of B will be something like this. So we can apply f here. So basically the way you define what's the mapping of arrows is by post-composing with it. So we have an element here in D in this category D, and then we post-compose with this f. So I don't have the example in Haskell. I will add it, but does it make sense to everybody? How you build this? This is gonna be a very, as I said, very, very important functor later on. Yes?
So what I'm not sure on is like, where is A coming from?
This A,
yeah.
You mean? Yeah, that's anything. So I'm saying for every object A in C, the way we map f to A is each A. So as I said, I mean, usually you will write something like this: f of x equals D to x. But I said we usually use Haskell-like notation and with the parentheses, but it's saying the same thing. We are just defining a function and objects which does this.
Okay.
Okay, so I have one more minute to tell you a couple of things. So, first of all, and you were already expecting this, I guess. It doesn't matter. I don't. Okay. Functors compose. So if we have a functor from F to D to E, we can have a composed functor G to F. So everything, again, composition is intrinsically in this category theory. You can even go farther, because if you take a category such as the objects are categories and the arrows are functors, this is itself a category. So this is the category of categories, and you have to go around many things to avoid this kind of Russell paradoxes, but you can actually build this kind of stuff. So the whole notion of what categories are form indeed a category in a very nice notion. So the last thing, yeah, if I can use 2 more minutes. So how does this relate to a functor in Haskell? Because in a functor in Haskell, we don't have all these things. We don't have any categories, we don't have any of this thing. We only go and say, well, if we have a functor f, I give you a to b, and you give me f of a to f of b. So a functor in Haskell is what we call in category theory an end functor. Is a functor always from a category to itself. So a functor in Haskell always goes from this category Hask I've defined to the same category Hask again. So it's not the very general notion of functor, is only an end functor. And actually, it's not even any kind of end functor. It's a very kind of a special way in which, remember, here you have a way to map objects and a way to map arrows. But here we only define how to map arrows. Why? Because if we are defining the Haskell notion of functor, the action on objects has to be predefined, and it's always applying a type constructor. So this function on objects is always going to be, if you take a type A, you get maybe of A. If you take a type or list of A or something, but it's always applying a type constructor to it. So you cannot, it's not this general notion, it's just an end functor where the object part is actually this predefined thing. But you can still use all the theorems because these are still functors. Yeah. So as I didn't have time to show you the next step, which is functors. So if you have 2 functors, you can actually go from one to another, and this is what we call a natural transformation. But we will see it tomorrow, no worries. So I will post the link to the questions on Slack, and feel free to come to me at any point and just bother me about all this stuff. So see you tomorrow, and I think you need to drink more coffee for the next session.